This grid has 64 numbers, but SVD, Singular Value Decomposition, reveals that 96% of the information lives in just one pattern, one outer product, one pair of vectors. The rest, mostly noise. Add just one more pattern and the reconstruction is nearly perfect. Look at the singular values. The first one, sigma 1, is over 1,000. It towers over everything else. This is the mathematical key that lets AI compress images, discover hidden structure in data, and find the dimensions that truly matter. The same math powers Netflix recommendations, face recognition, and the compression of the largest language models on Earth, SVD and PCA. In episode 1, we learned that matrices are linear transformations. They move every point in space all at once. Now take this matrix A, 2, 1, 1, 2. It's symmetric. Here's a unit circle, every point at distance 1 from the origin. And these colored arrows are two special directions we'll discover in a moment. Now watch what happens when we apply this transformation. The circle becomes an ellipse. The gray arrows change direction. But this blue arrow, it didn't rotate at all. Lambda 1 equals 1. It stayed the same length. And this gold arrow, same direction, but 3 times longer. Lambda 2 equals 3. These unchanging directions are called eigenvectors. The scaling factors are eigenvalues. The equation that defines eigenvectors is beautifully simple. A times v equals lambda times v. The matrix just scales the vector. To find eigenvalues, we solve the characteristic equation. Determinant of a minus lambda I equals 0. For our matrix, this gives lambda squared minus 4 lambda plus 3, which factors as lambda minus 1 times lambda minus 3 equals 0. Lambda 1 is 1. Lambda 2 is 3. Our matrix A is symmetric. It equals its own transpose. The spectral theorem guarantees two crucial properties. All eigenvalues are real numbers, and the eigenvectors are orthogonal, perpendicular to each other. v1.v2 equals 0. These natural axes of the matrix will become the foundation for everything that follows. SVD, Singular Value Decomposition, is one of the most powerful ideas in all of mathematics. It says that any matrix, no matter its shape, can be broken into 3 pieces. First, a rotation, then a scaling along the axes, and finally another rotation, A equals U, sigma, V transpose. Let's see this with a concrete example. Take this 3x2 matrix B. It's not square, so eigendecomposition won't work, but SVD decomposes it perfectly. The first singular value, sigma 1, is the square root of 45, about 6.71. Sigma 2 is the square root of 5, about 2.24. These come directly from the eigenvalues of B transpose B. Now let's see SVD geometrically. Take this 2x2 symmetric matrix G. Its singular values are 3.62 and 1.38. Step 1. V transpose rotates the input. The circle is still a circle, just aligned to new axes. Step 2. Sigma scales along those axes. The circle stretches into an ellipse, 3.62 in one direction, 1.38 in the other. Step 3. U rotates the ellipse to its final orientation. 3 simple steps. Any matrix, any shape. This is what makes SVD so extraordinary. Eigendecomposition only works on square matrices. SVD works on any matrix. Rectangular, ranked, efficient, anything. And the connection is elegant. Singular values are simply the square roots of the eigenvalues of A transpose A. Eigenvalues reveal the structure of square matrices. SVD reveals the structure of everything. Now that we have SVD, we can do something remarkable. Instead of keeping all the pieces, we keep only the k largest singular values and their vectors. Think of it as stacking layers. The first layer, sigma 1 U1 V1 transpose, captures the most important pattern. Each additional layer adds finer detail. But here's the question. Is this the best we can do with k layers? The answer is yes, and it was proven in 1936. The Eckart-Young theorem states, among all matrices of rank k or less, the truncated SVD minimizes the approximation error. This is not just a good approximation, it is the optimal one. No other method, no other matrix of the same rank can get closer to the original. We can measure exactly how much information a rank k approximation captures. It's the ratio of the squared singular values you keep to the total. And the error? It's simply the square root of what you threw away. Here's the key insight. In real-world data, singular values often decay rapidly. That means a small number of components captures the vast majority of the information. In 1936, Carl Eckart and Eckart-Young published this result in the journal Psychometrica. Nearly 90 years later, it remains one of the most important theorems in applied mathematics. Now let's see what this theorem can do with actual data. Here are 64 numbers arranged in an 8x8 grid. Think of it as a tiny grayscale image. Brighter values are lighter, darker values are darker. On the right, it's singular values. Notice how sigma 1, 1024 completely dominates. The rest are tiny. Now keep only the first singular value, rank 1. Every single cell becomes 128. A uniform gray. And yet this single number captures 96.4% of the energy. Why? Because 128 is the average brightness. The dominant pattern is just the mean value across the entire image. Now add just one more pattern, rank 2. The reconstruction is nearly perfect. The error drops to 0.9, 2 singular values, 2 patterns. That's all it takes to encode this entire 8x8 image. Now imagine a real image. 512 by 512. That's 262,000 values. At rank 5, you store only 5,125 values, a 51 times compression. At rank 50, 51,250 values, 5.1 times compression, and the image is visually almost identical to the original. This is the power of SVD. Real-world data is compressible because singular values decay. PCA, Principal Component Analysis, asks a simple but profound question. Given a cloud of data points, what is the most important direction? Here are 12 points in 2 dimensions. They're scattered, but not randomly. There's a clear pattern, a direction along which the data spreads the most. First, find the center, the mean of all points. Now, the direction of maximum spread. This is PC1, the first principal component. It captures 94.9% of the total variance. PC2 is perpendicular to PC1. It captures just 5.1%. Almost all the information lies along a single direction. Now project every point onto PC1. Drop each point down to its nearest spot on the principal axis. We've gone from 2 dimensions to 1, and we've kept 94.9% of the information. What did we lose? Just the tiny spread perpendicular to PC1, 5.1%, mostly noise. Here's the beautiful connection. PCA eigenvalues equal SVD singular values squared divided by n-1. PCA and SVD are the same math, just viewed from different angles. A scree plot makes this visual. PC1 towers over PC2. The elbow tells you where to cut. Carl Pearson discovered this in 1901. Harold Hotelling coined the term principal components in 1933. In 1991, Turk and Pentland showed how SVD could recognize faces. Every face image is a high-dimensional vector. Apply PCA, and you get Eigenfaces, the principal components of the face space. Every face is a recipe. The Eigenfaces are the ingredients. The weights are the amounts. A 256 by 256 image has 65,536 dimensions, but just 50 to 150 Eigenfaces are enough for recognition. The Netflix prize showed SVD's power in a different domain. Users rate movies, but most entries are missing. The ratings form a sparse matrix, question marks everywhere. Low-rank SVD fills in the blanks. Your preferences live in a low-dimensional space. Just 20 to 200 taste factors explain what you like. The same idea compresses the largest AI models on Earth. LoRA, low-rank adaptation, replaces massive weight updates with small low-rank matrices. W equals W0 plus B times A. Billions of parameters, but only millions of updates needed. And when you apply SVD to matrices of word co-occurrences, you discover something magical. Words arrange themselves by meaning. That's the story of episode 10. The story of SVD spans more than 150 years. In 1873, Eugenio Beltrami published the first derivation in an Italian mathematics journal. 1 year later, Camille Jordan independently derived a more complete version. In 1901, Carl Pearson invented PCA as a geometric tool. Harold Hotelling formalized it in 1933, coining the term principal components. And in 1936, Eckart-Young proved that truncated SVD is the optimal approximation. In 1965, Golub and Kahan created the first numerically stable SVD algorithm, making it practical for computers. Turk and Pentland brought Eigenfaces in 1991. The Netflix prize in 2006 showed the world that matrix factorization could predict your taste in movies. And LoRA in 2021 uses low-rank decomposition to fine-tune the largest language models with a fraction of the parameters, from bilinear forms in an Italian student journal to compressing the world's largest AI models. Let's bring it all together. First, eigenvectors are the natural axes of a matrix transformation, the directions that don't rotate. Second, SVD decomposes any matrix, square, rectangular, anything, into rotation, scaling, and rotation. Third, truncated SVD gives you the optimal low-rank approximation. The Eckart-Young theorem guarantees it. Fourth, PCA finds the directions of maximum variance, and it's computed through SVD. And fifth, from image compression to Netflix recommendations to LoRA, compression is the key to intelligence. 9 episodes, from vectors and matrices in episode 1 through gradient descent, Bayes' theorem, backpropagation, softmax, universal approximation, loss landscapes, and convolution, to SVD and PCA in episode 9. Each episode builds on the last. Each concept connects to every other. And next time, we'll discover how AI learns the meaning of words. Embedding spaces.